Okay. So, now we have to make A1 is equal to A2, right, area A1 is equal to area this thing A2. So, and we have to find out delta CR. So, what we will do, look, before proceeding further, A is equal to that original graph P is equal to P max sin delta, that means this graph, the green color one, this graph. Now, you let the graph B, that is B, there is a black one, this black one B1, B is equal to say some constant K1 into A. That means, because this this and A is equal to P we are writing here, because graph A is equal to P. So, it will actually K1 into P max sin delta. Later we will see that K1 K2 all can be obtained, and this graph C, that means your this one, this is graph C. Oh, there should, listen one thing, there should not be any confusion, this is graph C and this is at point C. So, there should not be any confusion, right. And this one graph C is equal to K2 into A is equal to K2 into P max sin delta. So, say and K2 is greater than K1, because this graph C, if you see this power is always greater than your what you call this during, I mean post fault or after fault, this power curve always above this graph. So, K2 is greater than K1 or otherwise K1 less than K2, and at delta is equal to delta 0, Pi is equal to, that is Pi is equal to P max sin delta 0. So, at delta is equal, at this is the point green color, that A point, Pi is equal to P max sin delta 0. Now, that area A1 is equal to A2 means that is you take delta 0 to delta CR, because this is area 1 you have to integrate. So, integrate delta 0 to delta CR, then this is your Pi graph. So, this is Pi minus the curve B, that means this curve curve B, Pi minus B, and B is equal to K1 into A, that is K1 P max sin delta, we will come to that, is equal to this area A2, that is limit integration delta CR to delta max, integration delta CR to delta max, then C minus Pi, this is the curve C and minus this line Pi, this Pi line. So, C minus Pi d delta. So, that means delta 0 to delta CR Pi minus K1 into P max sin delta, this is d delta actually, this is into d delta, right, is equal to delta CR to delta max, C curve is equal to K2 P max sin delta, here it is. So, that is delta CR to delta max K2 P max sin delta minus Pi d delta. So, if you integrate, and in this expression if you substitute Pi is equal to P max sin delta 0, and I repeat delta max is equal to delta m. So, if you substitute here Pi is equal to P max sin delta 0, integrate and simplify, you will get cosine delta CR is equal to 1 upon in bracket K2 minus K1 into delta max minus delta 0 into sin delta 0 plus K2 cosine delta max minus K1 cosine delta 0, this is equation 55. This one you will get it, right, that this is the from which you can find out what will be the delta CR. So, this integration I am not showing, this is easy. So, you can make it of your own, a simple thing. So, next is we will take an example now. So, I think whatever mathematical derivation was there, everything is there for this course. Perhaps it is over, right, perhaps it is over as far as theory is concerned, and now we will come to 2-3 numericals, good numericals. So, first one is, look at that, first one is that example 8, a 50 Hz synchronous generator capable of supplying 400 megawatt of power is connected to a large power system and is delivering 80 megawatt when a 3-phase fault occurs at its terminal. So, determine A, the time in which the fault must be cleared if the maximum power angle is to be 85 degree. Assume H is equal to 7 megajoule per MVA on a 100 MVA base. B, the critical clearing angle. So, from equation 48, Pi is equal to Pm sin delta 0. you know this all equations already I have given, but let me search that where equation 48, otherwise you know this from the sine curve, you know this, it is equation 48, just hold on, otherwise that is not a problem, you know everything. So, just hold on, if I get it I will show you that P m is equal to this thing, here it is, you know this, that P I is equal to P max sin delta 0, this is equation 48. So, in that case it is 3 phase. So, P I will be 80 by 3 megawatt and P max will be 400 by 3 megawatt, and then sin delta 0 you can find out 80 by 3 divided by 400 by 3. So, you will get delta 0 is equal to 11.54 degree or 0.2 radian. Now, it is given that maximum power angle is to be 85 degree, this is given. So, if it is given, so that is delta 1 is equal to delta m is 85 degree, that is 1.48 radian. Therefore, from equation 49, that means this equation, this is your equation 49, that cosine delta c is equal to cosine delta 1 plus delta 1 minus delta 0, but delta 1 is equal to delta m is equal to 85 degree is equal to 1.48 radian. That means, you can write cosine delta c is equal to same formula I am rewriting here. So, everything put in radian. So, it is cosine 1.48 in bracket, it is delta 1 minus delta 0, this is also radian, 1.48 minus 0.2, then sine 0.2, these are all radian. That means, delta c you will get 1.22 radian, that is your delta c. And from equation 52, that your critical, your what you call that clearing time expression. So, this is your 51, just let me see if I find it, that your 53 here. This is equation 52, the T c expression is given, this is equation 52, and from equation 52 T c is equal to same equation we are rewriting, and you put all the values, H value delta c minus delta 0 upon pi a p I. So, H is given 7, so 2 into 7, delta c we have computed, right. Your here I think while writing I have made a typograph, I mean writing error. I think it will be your, just hold on, that where is that formula, it will be delta c minus delta 0. So, it will be your this delta c, actually it is 1.22. So, I have made by mistake 1.48, I have taken this value by mistake delta 1, right, it will be actually 1.22, I think answer is correct. So, T c is equal to 0.377 second or 377 millisecond, but I will request you, I do not have calculator here now, right, whether I computed it using 1.48 or 1.22, but correct is 1.22, I corrected, but if answer is little different, you please check with the calculator, this is my request to you, I do not have calculator here. So, this is your T c is equal to what, it may be 37 millisecond, or if it is based on 1.48, then this answer will come, but this is not correct answer. So, basically it will be 1.22, I have now corrected. So, please make it, otherwise this is the answer, and right. So, and from equation 53, this one, then your you will get that equation 53 cosine delta C r was given is equal to pi minus 2 delta 0 sin delta 0 minus cos delta 0. So, delta is actually cos inverse of the all these thing. You substitute all these values here, you will get critical clearing angle will be 115.46 degree or 2.01 radian. So, next is your example 9. Next one is, suppose a synchronous generator is connected to a large power system and supplying 0.45 per unit megawatt power of its maximum power capacity. A 3-phase fault occurs and the effective terminal voltage of the generator becomes 25% of its value before the fault. But when the fault is cleared, the generator is delivering 70% of the original maximum value. Determine the critical clearing angle. You have to find out the critical clearing angle. So, whatever we have taken before, actually K 1 and K 2, we have seen that K 1 actually P max during the fault and ratio of P max before the fault, because we have taken your your curve A, B and C. Curve B we have taken it is k 1 into your P max sin delta. So, k 1 actually P max during the fault, the ratio what is the during the fault, what is the maximum value of the power P max divided by before the fault, P max before the fault, that is k 1, and k 2 is equal to P max after the fault and P max before the fault. If I get it here, if I let me find it out, if it is here I can show you, but I have already told you all these things. Just hold on. If I get it here, then it is okay, otherwise you know this. Here that A is equal to, this is your before fault, and this one that B is equal to, it is your during fault, and C is equal to, it is after fault. So, therefore, K1 will be whatever that this thing will come your P max during the fault, and denominator always is P max before the fault, and K 1 is equal to P max during the fault and K divided by P max before the fault, this ratio, and K 2 is the ratio of P max after the fault divided by P max before the fault. From here only everything is given here only. Therefore, from equation 55, this is the equation 55, we are rewriting the whole equation here. So, initially the generator is supplying 0.45 per unit megawatt of P max. So, initially it was supplying, that means your this is actually Pi, as initially it was supplying your 0.45 per unit megawatt of P max, that means this is actually your Pi actually 0.45 P max is equal to, you can write P max sin delta 0. So, this is your, you can write at operating point your at a operating point anywhere you take, that is your this thing, for example, any operating point here, this delta 0, right. So, your Pi is equal to 0.45 your P max is equal to P max sin delta 0, P max will be cancelled. So, delta 0 will become 26.74 degree or 0.466 radian. Now, P max is equal to magnitude E g into V t upon x d. Now, when the fault occurs, when the it is given in the problem, when the fault occurs, the V t becomes 0.25 V t, right. So, in that case your K 1 will be 0.25, because everything will remain same, only this 0.25 will be there. So, that means power will from its original value, it will come down to 25% actually, that is why K 1 will be 0.25. Now, after the fault is cleared, K 2 will be 0.70, because that is also given in the problem, that is also given in the problem, that when the fault is cleared, generator is delivering 70% of the original maximum value. So, determine the critical clearing angle. I mean, if you look at the graph, initially it was P max, but during the fault it was actually 0.25 P max, and when fault is cleared it is actually 0.7 P max, right. So, this is the philosophy. So, from this graph you can make out, this is P max, this is 0.25 P max, and this is 0.7 P max, this blue one, and black one is 0.25 P max, and this is P max sin delta. So, if you take all this data, that then K 1 is known, K 2 also then known, it is 0.7. So, therefore, P I is equal to K 2 P max sin delta m dash. Just hold on, I have to take that graph again. So, here it is. So, this is actually this blue curve you take, this blue one, that it, and this blue horizontal line, that Pi line, and this is delta m dash, Therefore, after the fault is cleared, so this is the blue line, it is in operation, this is the power that supplied by your what you call from the generator, P max is equal to sin delta your into your whatever fraction is come 0.7. So, this is that graph. So, and it's the horizontal blue line, the intersection is delta m dash. So, that is why after the fault is cleared K2 is 0.7 and we have Pi is equal to K2 P max sin delta m. So, this is your graph C actually, this is your graph C, this is your graph C, and here it is C is equal to K2 a K2 P max sin delta, K2 is equal to 0.7. Then this one Pi is equal to K2 P max sin delta m dash. So, that means this point delta m dash means this point. So, in that case you compute what is your delta your m dash. So, Pi we can write sin delta m dash is equal to Pi upon K2 P max. So, Pi is your sin delta is equal to 0.45 P max divided by 0.7 P max. So, that is actually coming 0.45 by 0.7. So, in that case you will get delta m dash is equal to your 40 degree, because Pi is equal to 0.45 P max, it was given that 45% of that. So, Pi is equal to 0.45 P max. So, here we have put Pi is equal to 0.45 P max divided by 0.7 P max is equal to 0.45 by 0.7. This actually comes to delta m dash is equal to 40 degree or 0.698 radian, right. So, that means delta max, that means this is your delta max. So, delta max is equal to pi minus delta m dash, the delta max is equal to, that means from here the delta max is equal to pi minus delta m dash. So, delta m dash we have computed 0.698 radian, this we have computed, here you have computed. So, if you put it here it will be 2.443 radian, and in all this data available. Now, go back to equation 55. I have not rewritten that equation again, but it is equation 55, cosine delta CR is equal to 1 upon K2 minus your K1, then 2.443 that is delta max, right, your minus 0.466, then that is delta 0, that is sine of it is radian 0.466 plus your 0.7 cosine 2.443 that is K2 cosine 2.443 and minus 0.25 that is K1 cosine 0.466 that is delta 0, and if you compute all it will become is equal to 0.29. That means, delta critical angle will become 73.14 degree or 1.276 radian, right. Directly you can put it there and you will get this answer. So, this is the answer. Now, another one, this is this one among all, this one is the easiest one, but only you need delta star delta transformation. Now, I will show you the figure. Now, I hope this you have understood, right, that how to find out that your critical clearing angle or critical clearing time. Now, this is another example, it is a double circuit line. So, find the critical clearing angle of the power system shown in figure 15. I will give you for a 3-phase fault on the point tape. I will show you the diagram. So, generator is supplying initially 1 per unit megawatt power, initially it was supplying 1 per unit megawatt power under pre-fault condition, that is before fault it was 1. Now, this is the circuit connection, this generator, right, reactance is given 0.20, here transformer is there 0.05, all J are there not uttering again and again. This is line reactance 0.38, again transformer 0.05, this is also 0.05, line 0.38, 0.05 and 0.20. So, before fault line impedance was reactance was 0.38, but fault has occurred 3-phase fault in the middle of the line. That is why here also I have seen this side it should be half, this side it should be half. So, no confusion, total is in this line there is a fault and this side is j 0.19, this side is j 0.19, but total when there is no fault 0.38 and identical parameters, and this side voltage generator voltage is 1.20 per unit and this is infinite pass side. So, it is magnitude is 1 angle 0 per unit. So, now pre-fault condition when there is no fault. So, do not consider you put your finger here no fault is there. So, that means 0.2 should be added, J I am not putting again and again, it is reactance calculation, that is your pre-fault corporation, that is A, that means carb A. When look at this, when you are making A, B, C, you have to imagine this way that this is pre-fault graph A, when I will make x b, it will be during fault, and when I will make c, it will be after fault. So, a, b, c, this way we will do it, then we will not make any mistake. So, in this case, this is your double circuit. So, these two are in parallel. So, there is no fault, that means equal it is 0.38 plus 0.1, 0.05, 0.1. So, 0.48 and 0.48, these two are in parallel. So, it will be 0.224 and this side 0.2, this side 0.2. So, 0.4 plus 0.24, it will become 0.64 per unit. So, this pre-fault condition, this is pre-fault or operation, that x a will be 0.2 plus it is parallel equal. So, it will be taken half 0.05 plus 0.3 plus 0.05 by 2 plus this one 0.2. So, it is coming x a is equal to 0.64 and the graph A is that your pre-fault condition and voltage is given 1.2 and 1. Throughout this, these two voltage will not change. So, it will be 1.2 into 1 divided by x a. So, 0.64 sin delta is equal to, it will become 1.87 sin delta. That means, it will be your this graph, green color graph A. That is why I am making it P A, graph A, that means this will be your graph A. Similarly, now during fault, before that we have to compute also this delta 0 angle on the green graph, this delta 0 angle is also required, right, but P I is given 1, P I is given 1 per unit, this is given. So, in that case the delta 0 will be sin inverse 1 upon 8.75 because when P E is equal to P I operating at steady state, right, before fault. So, it that is 1 is equal to, because 1 is given, P I is equal to, that is 1.875 sin delta. The delta is equal to your sin inverse, that is delta is equal to delta 0 at this point, delta is equal to delta 0 at this point, delta is equal to delta 0. So, that means you will get delta 0 is equal to sin inverse 1 upon 1.875, that is given 32.23 degree or 0.562 radian. So, next is during fault. So, suppose fault has occurred at this middle of the line, second line here. So, this side should be 0.19, this side should be 0.19. So, if it is so, then you draw this diagram, fault has occurred at the middle of the line, this is 0.2 of this line will remain same, this line will remain same. So, j 0.05, j 0.38, j 0.05, this is j 0.05, but it will be half j 0.19, j 0.19, then 0.05, this is 0.2, this is generator side, this is infinite bus side, actually this is infinite bus side. Somehow I have made this thing, I have removed this, but this is infinite bus and this is your circuit connection during fault, right. So, this way you should, because fault has occurred at the middle of the line. So, once you made this connection, well, look at that, this is basically delta connection, you have to convert it to star. So, delta star connection you can make it of your own, I can give you the your final value, right. This is basically your just hold on, this is basically your delta connection. I mean I just write for you only this part is this is a delta connection. Suppose this is your fault, this is fault position, as this is your F, say I am just putting it like this. So, these two are there 0.05 and 0.19. So, this should be your j 0.24, this side also 0.19, 0.05, this is also j 0.24 and this is 0.35, 0.05, 0.05. So, 0.48. So, this side will be your j 0.48 and if you convert it to star, you convert it to star. If you convert it to star, this side will become your j 0.12, this is j 0.12 and this will become j 0.06. It just delta to star, you know how to convert, you convert it. So, if you convert it, then connection will be, this side will be j 0.12, this side will be j 0.12 and to the from here to the fault point j 0.0, that point F to 0.06. So, that means this one it is by, and with that this side it was j 0.20, this side also j 0.20. So, that means these two will be in series. So, j 0.2, j 0.12, this side j 0.12, j 0. This is j 0.06. So, this is the delta star conversion. Now, if you make this one, this is now star connection, because this side will be 0.32, this side will be 0.32, and this will be then this one will be j 0.06. So, this is now star connection. This one again you have to convert it, star has to be converted to the delta. So, right, if you convert star to the delta, these two I have not computed, no need, because here your generator is there, here this side is infinite bus is there. For power transfer we need only the x b, that is during fault this one is required, these two are not required actually. So, these two I have not computed. So, this is a star connection I am showing you, but you will do it, I am showing you. So, this is your star connection, this is your star connection, this side will be j 0.32, this side I have made it for you, this side 0.0 and this is your j 0.06, and this is your converted to delta, these two side not required, only this one is required, right. So, if we convert star to delta only that side, that x b. So, if you convert, then it will become that 0.2 0.12. So, 0.2 it is actually the formula is suppose R 1 R 2 R 3, then R 1 suppose we are star R 1 R 2 R 3, suppose we want to convert it to delta, start to delta, it will be R 1 plus R 2 plus R 1 R 2 divided by R 3. So, same way we have made it. Suppose for example, this is your this side is your x 1. So, 0.2 plus 0.12, this side is, if you say this side is your x 2. So, it is 0.12 plus 0.2, both are equal, plus product of these two divided by your x 3, that is your 0.06. So, if you make x b, it will be 2.3466 per unit. This is your what you call that delta conversion, this value, but this is not required for power transfer. This is not required at all, because nothing is here actually, voltage across is this one and voltage across is this one. So, only this one is required. So, once it is done, then and this voltage 1.2 and 1 always remain same, that means your electrical power P E B, that is during fault, it will be 1.2 into 1 divided by 2, that is x b, 2.3466 sin delta. This will become 0.5113 sin delta, that means this graph, this graph will be 0.5113 sin delta during fault, this graph. And now, post fault condition, when the fault is cleared, when this fault is cleared, this line is isolated, only this line will be there, this fault is cleared, then you have to find out that what is the value of x c, because we have to find out P E for curve C. So, this line is isolated when the fault is clear. So, in this case fault line is open. So, this line is not there, it is open, right. So, this line is gone, only this line is there. So, in that case just you add all the reactances, this one and this one, just add, because this line is open, right. So, in that case that faulty line is open. So, x c is equal to 0.2 plus 0.05 plus 0.38 plus 0.05 plus 0.2 is equal to 0.88 per unit. That means, for curve C, for this one, that is after fault, this curve for curve C. So, this is x c and P E C is equal to 1.2 into 1.0 upon 0.88 sin delta is equal to 1.363 sin delta. That means, this graph, the graph C is 1.363 sin delta, right. With getting all these things, so all the three graphs we have got, I mean power delivered during your pre fault, during fault and post fault, all we have got. Therefore, K1 will be we have told you that it will be P max during fault, that is 0.5113. This one, let me see, I have to search it. This is 0.5113, and this is we have got it, that before fault 1.87 pre fault condition 1.875, that is 0.2727. K2 is equal to your when your after fault, that is your 1.363, just now we have got graph C 1.363, divided by that your pre-fault condition max 1.875. So, 0.727. Now, you have to compute delta m dash. So, delta m dash actually this one, this is your delta m dash, that is the blue curve, that is the blue curve, right. This is your delta m dash, and in this is the intersection of this horizontal line and this blue one, this is your delta m dash. So, in that case that your delta m dash will be, because we have seen that C curve it is 1.363 when delta is equal to your delta m dash, that is 1.363 sin delta m dash. So, at that time this power, this is given pi is 1, this pi is 1, and when pi is 1 and delta m is equal to delta m dash. So, this graph will put that. So, in that case your delta m dash will be sin inverse 1 upon 1.363. So, that will come 47.19 degree or 0.8237 radian. Now, delta m is equal to delta max is equal to pi minus delta m dash, that means this one, delta max is equal to pi minus delta m dash, this one. So, we get delta max is equal to this one 2.317 radian, that means delta m is equal to delta max is equal to 2.317 radian or 132.75 degree. Once you got all this, then equation 55, from equation 55 rewrite this equation has been rewritten. Now, put k 1 value, k 2 value, delta max value, delta 0 value, you will get the delta CR. Once you put it, then this one you substitute all this value, all are radian, we have substituted all this in radian. That means, cosine delta CR will become 0.46363, that means delta CR will be 62.2 degree. So, results are summarized here for this problem, results are here, results are summarized, that delta 0 we got 32.23 degree, delta m dash we got 47.19 degree, delta CR we got 62.2 degree, and delta m is equal to delta max we got 132.7 degree. So, this is one, and another example you take. This is a short example, I mean small example. Suppose a synchronous motor is receiving 35% of the power that it is capable of receiving from an infinite bus. If the load is doubled, determine the maximum value of the load angle, right. So, it is said that it is it is given that synchronous motor receiving 35% of the power that is capable of receiving from infinite bus, but if the load is doubled, determine the maximum value of the load angle. So, from figure 7, if you go back, then I think I have figure 7 in front of me. This is my figure 7. So, it is P 0 is equal to P I 0 and this is P max sin delta. This is figure 7, from figure 7. So, P I 0 is equal to, it is given 35% of the power. So, P I 0 is equal to 0.3, P I 0 is equal to 0.35 P max, this is P max, this is P max. So, P I 0 is equal to 0.35 P max. Therefore, that is delta 0 is equal to sin inverse P I 0 upon P max, that is sin inverse 0.35 is equal to 0.357 radian, and now it has been doubled. So, P I will be equal to 2 into 0.35 P max, because it is given if the load is double now, right. So, determine the maximum value of the load angle. Now, it is double. So, it is P I is equal to 2 into 0.35 P max, that is 0.7 P max. Therefore, you have to compute delta 1, that is your delta 1. So, that is delta 1 is equal to sin inverse P I upon P max, that is sin inverse 0.7, it will become 0.775 radian. Now, in figure 7, delta 2 is the maximum load angle during the swinging of the rotor. So, in the this is figure 7 and this is the delta 2 is the maximum rotor angle, right. So, using equation 46. So, we are rewriting equation 46 here, the delta 2 minus delta 0, then sin delta 1 plus cosine delta 2 minus cos delta 0. Only here delta 2 is unknown. So, put all these value delta 2 your this thing sin delta 1, right. So, put all these value here. So, delta first I am writing this delta 2 minus delta 0 is 0.357, then sin delta 1 that is by your coming point say your 7, and then here it is given that delta 1 is equal to sin inverse 0.7, that means sin delta 1 is equal to 0.7. So, we are putting here sin delta 0.7, no confusion, plus cosine delta 2 unknown minus cos delta 0, delta 0 is equal to 0.357 radian. So, cosine 0.3 is equal to 0, that means delta 2 maximum we are getting 72 degree or 1.25 radian. So, this is that last example of this power system thing, stability, and finally, what is the conclusion. So, I have written something here that we can conclude that the transient stability of a synchronous generator during and subsequent to fault conditions depends upon the rotor swing and the critical clearing time. These are governed by the machine inertia and direct axis transient reactance. The overall system stability can be improved by appropriate control scheme such as turbine valve control, fast fault clearing time, appropriate excitation systems and FACS devices, that is flexible AC transmission devices, right. But those are the things that can be improved. Now, for power system stability studies, whatever we have studied, I mean little bit of steady state stability, and that is basically that gradual increase of the load, that is maximum your loading capability before losing synchronism. Then little bit we have tried to understand regarding dynamic or small signal stability, that is due to small system disturbances, and finally transient stability for single machine infinite bus system, that is for your for large disturbances. And we have also defined in this topic that what is infinite bus, and to have tried to obtain that your critical clearing time. So, with this, those who will be listening this last class, 1 or 2 line, that 1 or 2 few things before closing these courses, because this is the last one, that starting from the beginning, that structure of power system and various aspects of power system, and there are, and we have come to this transient your power system stability, and within the given your time frame, that we have tried to cover I think 9 or 10 chapters, although there are many other chapters in power system, and whatever we have tried, that all the your theories, particularly for classroom exercise, that so many all the theories and mathematical derivations all supported by good number of examples, and particularly for when you come to the iterative techniques, that is load flows or that little bit of optimal system operation, that is economic load dispatch. We know that in the classroom or in the exam hall, that it is a time consuming without computer, but at least 1 or 2 iterations you can try from your side quickly, that what is the result. So, in that in this lecture also I have shown I think 2 or 3 iterations, load flow also, Newton-Raphson load flow also, Gauss-Seidel also only couple of iterations, and optimal economic load dispatch also I have shown the step, but that is basically coding is required, not this thing, but we have tried to explain that these are way one can do it. But as far as classroom exam is concerned or your classroom exercise is concerned, that you should make 1 or 2 iterations that and make every step is correct. So, with this your feedback will be more important for me, and what I would like to tell, that if you find any mistake or any error, particularly that calculations, because all these numericals actually have been done by me. I mean before coming to this lecture also, that your delta star delta transformation maybe 2.5 hours back, I was calculating by calculator that whether everything is correct or not. So, if I make any mistake or any error is there in calculation, please mail me such that I can correct those numericals, and if anywhere any writing is error or anything I have missed it, that you please see this. Only for 3-phase fault cases, only my emphasis was to for Z bus building algorithm, and other things little bit of Thevenin equivalent, this that I pre-assume that these are simple thing, you know it. With this I have to tell you that thank you.